one more series that we get to study this year is a Taylor and Maclaurin series. At the end of this lesson, you'll be able to state the formula for finding a Taylor series centered at x equals a. All right, first of all, what is a Taylor series and a Taylor polynomial? We're actually going to be dealing more with a Taylor polynomial than a series that basically approximates the function on a particular interval. And you notice this is called a Taylor polynomial. It was actually introduced by Brooke Taylor in the year 1715. So he came up with this and it's caught on with everybody. Basically what a Taylor polynomial is, or a Taylor series, it's basically if you're taking a function, it might be a function that's semi-difficult to work with. What we're going to try to do is to come up with a polynomial that is similar to that function, that takes on the same characteristics, because polynomials are a lot easier to work with than some of the more complicated functions. So that's the whole purpose behind a Taylor polynomial or a series. You'll notice that it says a Taylor polynomial approximates the function, and a Taylor series equals the function on a particular interval. So the series is just, if we went out all of the terms of the polynomial, what would that final answer be? And we're going to when we do these, we'll basically be pretty much treating them as the same thing as we're going through. So if I say find a Taylor polynomial, or if I find a Taylor series, it's going to be pretty similar. All right, so let's get into exactly what we are doing when we find a Taylor polynomial. So this is just a it's going to show you how we get that, so hopefully it will make sense when we actually get into creating Taylor polynomials. All right, if a function f of x is approximated by a polynomial so basically what we're doing, we're going to take a function and we're going to approximate it by a polynomial. And if you remember, a polynomial is just terms added that each have x's, so this is x plus x squared plus x cubed all the way up to x to the n. So as an example, polynomial just would be like 3x cubed plus 2x squared plus 8. That is a polynomial. So that's what we're going to be trying to do for different functions, is write a polynomial that would be very similar to the function in question. All right, so basically what we're going to do, I'm just going to show you where this Taylor polynomial formula came from. If this is my function, and a sub 0, a sub 1, they are just some sort of coefficients in front of the letters. Okay, if I were to take the derivative of this function, keeping in mind that a sub 0, all of the a's are constants, the a sub 0, the derivative of that would be 0. The derivative of a sub 1x would be a sub 1. The derivative of a sub 2x would be 2a sub 2x, and then plus the derivative of this next one would be 3a sub 3x squared. I'm going to go one more. If we would have had a sub 4x to the fourth, we're going to have 4a sub 4x cubed plus dot dot dot, and if we went all the way out to the end, we'd bump the n out front, so we'd have n a sub n x to the n minus 1. Okay, so now let's say we found the derivative again. So if I took the derivative of this one, my a sub 1 drops out. I now have 2a sub 2 plus 6a sub 3x plus 12a sub 4x squared plus dot 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 dot. This next one we'd have n times n minus 1 a sub n x to the n minus 2. So we'll subtract another one from the power. Okay, if I were to do the third derivative, I then would have, this would cancel out. I'd end up with 6a sub 3 plus 24a sub 4x plus, and then we could keep going. Okay, so what we're going to do now is I'm just going to look at what if I decided for each of these I would like to plug in 0. So if I plugged in 0 into this original function for my x's, I would simply just get a sub 0. And then if I plugged in 0 and f prime, so if I plug in 0 for all the x's, I'm just going to be left with a sub 1. And then if I took the second derivative and plugged in 0, I would simply just get 2a sub 2. And if I found the third derivative of 0, if I plugged in 0 for all the x's, I just get 6a sub 3. Okay, now there's something that I'm going to do with this, and what I am going to do with this is, notice that this is the first and the second are solved for a sub 0 and a sub 1. Two things I'm going to do in this one. First of all, I'm going to put f double prime of 0 is approximately 2, could also be represented by 2 factorial, and just hang with me a second on that one. F triple prime 6 is actually 3 factorial. So you could guess the next one will have 4 factorial, and then we'll have 5 factorial, and so forth. And that's going to come into play in just a minute. All right, so now let's say I wanted to take this formula right here and solve it for a sub 2. So if I solve for a sub 2 is going to be approximately equal to the second derivative divided by 2 factorial. And here, if I solve this for a sub 3 is going to approximately equal the triple derivative at 0 divided by 3 factorial. Okay, so now what we're going to do is take this. We now are going to take this formula. Instead of putting a sub 0 and a sub 1 and a sub 2, we're actually going to put what we just found for our a's and put them in there. So a sub 0 we know is equal to f of 0, and then plus a sub 1 we know is f prime of 0, x plus, coming up here to this formula, a sub 2 is equal to, we found out that that was equal to the second derivative over 2 factorial x squared, plus the next one, we'd have a sub 3 was equal to the third derivative at 0 over 3 factorial. And then we could keep going and going and going. All right, so that's pretty much what we are going to be doing. And basically what we have just found is a Maclaurin polynomial. And you might be wondering, well, you were talking about Taylor polynomials, and now you are talking about Maclaurin polynomials. Maclaurin polynomial is basically just a special type of Taylor polynomial. If I center the problem at x equals 0, so I'm just looking at the function right around x equals 0, I really don't care what's happening on either side of it, and I'll actually show you a picture of that in a minute. It's going to be called a Maclaurin polynomial. So just based on where the center is, we'll either call it a Taylor polynomial or a Maclaurin polynomial, even though they're really all Taylor polynomials. All right, so a Taylor polynomial, a more specific type, we don't have to center it at 0. We can center it at any x value, and we'll call that x value a. So all I'm going to do with that formula that I just had, instead of 0 being my center in that formula, we had f of 0. Since my center is now going to be a, we're going to put f of a, and then plus, the next part of it was f prime of a. And remember it said x, but now since we're centering it at a, we're moving it, we're going to put x minus a, and then plus will be the second derivative at a. We'll have x minus a squared. It's still over 2 factorial. And then plus f triple prime a, x minus a cubed, all over 3 factorial. And then we could keep going. So the way that this would look like in sigma notation, if I would actually want to do a series instead of just the polynomial formula, this would just go from n equals 0 to infinity. We're just going to basically take this formula, we're going to get f. The derivative, we're just going to take, if we went out n spaces of a, x minus a to the n power this time, and then it would be over n factorial. So that would be, if I had to write a series formula, that's what it would look like. Okay, so that's pretty much what we are going to do. If I ask you to create a Taylor polynomial, you are going to plug the information from your function into this formula. Okay, and just one note, the order or degree of the highest derivative is the order degree of the Taylor polynomial. So if I ask you to find a Taylor polynomial of degree 3, we will go out to the third derivative. And so hopefully now at least you're familiar with the formula. Our next video will get into some examples of creating Taylor polynomials.